Well, hello everyone. I'm Mike Laposata. Many of you know me, um, and we have worked together. Let me say I'm delighted to do this, and I have learned so much during the COVID time. My scientific work for 30 years was being a fatty acid biochemist, so this step into virology has been very educational for me. And I've followed it all very carefully. And it's very clear that it is getting more complicated. And it is easy enough to understand the variants when they are presented to you in a way that's understandable. There's so much information that's coming, it's hard to know what it all means for us. So that's going to be the goal of this presentation. And we're going to talk about the new variants and how that affects the tests we perform and how well the vaccines work. So the outline looks like this. I'm going to tell you about the virus, some structural issues, and then focus on the structure of the spike protein, because this is where the antibodies are made for the vaccines so that we can interrupt the binding of the virus to the host cell. We're going to talk about that process whereby the virus gets inside the host cell, and then we're going to focus on two variants at first, the UK variant and the South African variant, and then we're going to go to talk a word about everything that's out there, all kinds of different variants and how they're being classified, and we're going to throughout say something about how the variation in the proteins of the virus, the spike protein of the virus, affects the efficacy of the vaccine. So here are our big concerns, and in fact, there's legitimacy in each one. Is there increased transmissibility when we get a variant? Yes, that happened. Is there an increase in illness severity? That happened too with a variant. Does it look like one of the vaccines has lost some of its effectiveness as a result of a mutation in the spike protein? Yeah, it looks like the South African variant did some of that with one of the vaccines. How about these antibody methods, like the one Trump got, where he gave antibodies to individual proteins in the virus? Does that get affected by any of this? And the answer is that has happened too. And the other question is, what about our PCR assays? Are they going to get altered such that every test will be negative, which of course would be horrific? So we've seen a bit of all of these, so let's talk about the details of each one. So let's start with the structure of the virus. This is a picture that's always seen, and of course, we notice these big red outpouchings, and these are the spike proteins of the virus. And so we're going to focus most of our attention on the spike protein, but I want to introduce you to all of what's inside first. So take a look at this picture. This is taking that virus and slicing it in half. So now we can see the inside, and we can get a better look at the membrane too. So the first thing to point out here are that there are four main structural proteins. That is, they make a protein that actually is the girders of this virus, like the girders of a building. And the spike protein is the biggest one, shown in red, but there are two others, something called the membrane protein and another one called the envelope protein, that are in the membrane of the virus. And I would say, for the most part, those have not been implicated in a significant way in, in problems with transmissibility or vaccine efficacy. But there is one other structural protein where we're beginning to pay more attention to changes that might affect vaccine efficacy, and that's the one on the inside. And you'd say, what? How is that? The virus gets in, you'd get an immune response to the things that are sticking on the outside. Except remember, when there's a viral infection, you're going to break open viruses. All of these proteins are potential immunogens. And the protein called nucleocapsid protein, which is holding the RNA, remember this is an RNA virus, holding the RNA together, also has immunogenicity, and it's also mutated. So there are other proteins in there that are not structural. For example, you need a protein, as shown in this slide, that is going to be important in the replication of the RNA. There it is on the top with a blue arrow. It says RNA-dependent RNA polymerase. You need that. It's a non-structural protein. So let's take a look at the genome of the SARS-CoV-2 virus. And so in the center part of this slide, you have what we just saw a minute ago, the virus sliced in half. Now what we're going to do is take that RNA that's on the inside, stretch it out, and make it a circle. So first thing you're going to notice is there are 4 structural proteins that have genes. And the one on the right that's red says spike protein. You can also see the membrane protein, M, and the envelope protein, E. And you'll notice that the nucleocapsid protein is there as well. Now, that's not the biggest part of the genome. The biggest part of the genome are these non-structural proteins. So starting from the yellow at 6 o'clock and going up toward 12, you notice there are a whole bunch of non-structural proteins in something called open reading frame 1A. And then there's the RNA-dependent RNA polymerase in open reading frame 1B. And if you just count, there's a 1A, 1B. And then if you make spike protein too, you'll see they go sequentially and they're numbered consecutively. So there are lots of genes here, and the question is, if you mutate something, not just in the spike protein, how does it affect transmissibility and severity of illness? So here is now that circle spread out into a line. And really, the point of this is to show you that the structural proteins, those 4, including the spike protein, are really a relatively small percentage of the genome of the SARS-CoV-2. So there's a lot of similarity relative to other coronaviruses that we'll say about in a minute. So let's get to the structure of the spike protein. And so here it is, and I'm going to show you something that looks like this. Can they see me? Okay. So you can see on the top, I made this strawberry, and this is the spike protein. Ah, yes, I can see now. Very good. Got it. So thank you. So thank you right there. So the top part of this is the spike protein, which is that big cluster of yellow, and the brown stick on the bottom is the other part of the spike protein that actually inserts into the viral membrane. So let's take a look at this. You'll notice in the left part of this slide, there's something that delineates S1, that is this top part, from S2. Now let's take a look at the different parts of the S1 segment. So the first part that I want to show you is this at the very top. And you'll notice I put 3 white spots here. And these 3 white spots are the receptor binding domain. So these receptor binding domain portions bind to the host cell receptor. So there you see it binds. So you can imagine that anything that affects this part would be very important because it could increase transmissibility if it binds better, right? Or what if it mutates and now this top part doesn't do well at all and therefore it can't bind? And what if we make antibodies because we got a vaccine to the spike protein and that antibody is right there at the receptor binding domain and you're trying to get it into the host cell, but you can't because there's an antibody there. So that is the rationale of making the antibodies and trying to get antibodies, especially in the receptor binding domain. So that's the top part of the yellow portion that says receptor binding domain. Now, underneath that is another important part of this spike protein, and it's called the fusion peptide. And the fusion peptide is actually down toward the bottom of this strawberry. And the reason why that's important, which you'll see in a minute, is that to get inside the cell, you have to bind to the receptor binding domain, but it's actually another connection at S1 to the host cell that allows this virus to get inside. So the fusion peptide, also important. So you would think if you mutated something there, that might be important. If you mutated it in the wrong direction, maybe the virus can't be infectious at all. And it turns out most of the mutations take away from the virus being able to get inside the cell. So then there's the stick part, which is a bunch of protein chains. Now, let's talk about this, looking at it with actual amino acid chains. So if here I am wearing this shirt. What's this shirt made up? It's made up of threads. So you can look at it and you could hold it and say, oh, there's a shirt. But the reality is, if you look closer and closer, you'd say it's made of threads. Well, that is what all these proteins are made of. And it turns out that the spike protein is 3 identical chains that are interwoven to make the spike protein. And you see one is depicted in gray, one is red, and one is blue. So here is taking a look at it, not as the chain, but now looking at it sort of as the shirt. And you get an idea. The bottom part is the part that's stuck in the virus. So it's this part embedded in the virus, right? And now we're looking at it so that the top of the spike protein is at the top of the strawberry. And so the chains are not small, 1,273 amino acids. And so what happens? So I want to take you back now away from the molecular and up to the virus and cell level. So there you go. This is somebody who was breathing in something. South Africa, this could be any viral infection with coronavirus. And you see the yellow viruses on top of the blue host cells. And so what happens? Well, here's what happens. All those viral particles stimulate an immune response. So your body is saying, I'm going to make an antibody to the spike protein. I'm going to make an antibody to the nucleic acid. I'm going to wipe that out. So your body's trying to fight it. And one of those viruses, just by chance, because replication is not perfect, changes a nucleotide at the level of the RNA such that you make a different amino acid. And if that happens in the gene for the spike protein, now you have a change in the spike protein. And will that matter? It absolutely will. So, not for every mutation, but for many. So all it takes is one of those viruses in an infected person to mutate. So bottom line, please everybody get vaccinated, right? I mean, because if you don't get this infection in the first place, you don't have the pressure to create a mutated virus to make the next variant, right? So here's what happens, right? It explodes. Now we're in big trouble. So that's what we want to prevent. That's what the variant is trying to do. And there are thousands and thousands of variants, but only some of which are now variants of concern. So now let's get back to the details of how this spike protein, again red, and now the spike protein is pointed down, so it's hitting the receptor on the cell, so it looks like this, right? And as I pointed out earlier, that receptor binding domain where the red meets the blue, very important. If you're going to mutate it in a way that makes it less effective. Put those antibodies in the way right there. But this, I wanted to show you, and so what I'm going to do now is show you why the rest of the spike protein is important. So the virus is shown in the upper left. There's a circle, and you can see the RNA inside. So if you cut off the spike protein, now I'm going to turn it right side up, so you see the 3 salmon-colored balls at the top. That's S1, so it looks like this, right? But as you go down S1, right, and then you get into this part that's S2, you can begin to see that it's not only the receptor binding domain that counts. As I pointed out earlier, the receptor binding domain, of course, binds to the host cell, but you notice how in the bottom part, as you go from the left to the right, you see that the spike protein binds, but then it has to flip-flop some and land at this fusion peptide, and then it can get inside the cell. What is the meaning of that? The meaning of that is, what if I have an antibody that's on the side of the spike protein? What if it's on this side of the spike protein? And now what happens is, there it is, I have to get over, well, if there's an antibody in the way, it's not going to get in there. So I don't just have to have antibodies in the receptor binding domain. I could have them any place on this spike protein and potentially stop the virus from getting inside the cell. So if there are changes on the outside here, not just receptor binding domain, and the antibodies don't bind anymore, that's not a good thing, because these antibodies on the outside are going to be important too. So I'm going to tell you about variants, and I'm going to come up with my own nomenclature, which is to name all the variants by people's names. And so the way this nomenclature works is that the amino acid that was the first amino acid in the original virus it's got a one-letter code, and D happens to be aspartic acid, and it is at position number 614 in that long chain. Remember, it was 1,200 and some residues, so it changed to a glycine, and that was in the spring at the very beginning. So if you looked at it by the color, right, type A, type B, type C, you can see the spike protein is changing colors. So for this mutation, I call it DUG because it went from aspartic acid to glycine, and that's D to G. And so, so what is the meaning of that change? Well, the D is aspartic acid or aspartate. That's negatively charged, and it's replaced with glycine, which is nonpolar. Now, you would say, well, 1,200 different amino acids. You think one amino acid change could make this different, maybe more transmissible? Well, what about this? This is sickle cell anemia, and that is hemoglobin, and this is one of the amino acids, and it changes. It's not aspartic acid, it's glutamic acid, negatively charged amino acid, and it changes to valine, which is nonpolar. It looks almost like sickle cell anemia. So here's the way this works. So I show you this as a loop of protein, and if you could imagine me, right, my body as being part of an amino acid chain, and from my feet to my head is the basic line of the protein. You'll notice this has a loop though. So all proteins have loops. So somebody is standing on my head, and then somebody is standing on that person's head, and we are all lined up. And let's say that the loop comes around like this, and now all of us, each individual amino acid has something called an R group, and that's where the charge is. So let's say my right arm is the R group. So there it is. This R group could be positive, it could be negative, it could be mostly positive, that is polar but positive, and or polar negative, or it could be nonpolar. So I got 5 choices. And remember, positive and negative, you're going to bind. 2 hydrophobics, you can connect. But what if I changed from, say, a negatively charged D and DUG, aspartic acid, to a glycine, which is nonpolar? Then you see the first connection in the upper right in this loop. It's got an R group that's positive on one side of the loop and an R group that's negative on the other side of the loop, which means that's how the 2 parts of the loop stick together. Now, of course, it's way more complex than this. There you go. That's a tertiary structure. Look at all the interactions between the R groups that give this the right shape. They give this the shape of a spike protein. So here are 20 amino acids, and you can see 10 are nonpolar, 5 are polar, 3 negatively, 2 positively polar, and then there are 3 positively charged amino acids and 2 negatively charged ones. So here's DUG, and you see the bottom part under the red arrow. It was clear that when the aspartate was replaced by glycine, the virus was more infectious. Why did that matter? It meant that when you went to a party and one person had it, DUG spread all around the room, but its precursor was less likely to be transmissible. And how fast did this happen in the United States? Look at February. So things were coming in February from China, and we were in the D part. But when that D became a G, look how fast it came. At the end of February, by the beginning of April, we were pretty much all into the DUG version with lots more transmissibility. So that was the first change. Now let's talk a little bit about the UK variant. And there are different terminologies. I'll show you how they use the terminology in a minute. But it's called B.1.1.7. And the first thing to show you about this is what happened in the UK, the United Kingdom, and how fast it did. So take a look on the x-axis for our Thanksgiving. So toward the end of November, at that time, the UK's percentage of this variant was small. It was about 2%. And look how long it took before it was up well above 10%. And of course, it then became the dominant strain and created a new spike. That is a new spike in cases. And that's not even Christmas. So it only takes about a month to 6 weeks for a variant to take over if there's a lot of transmissibility. So now let's take a look. Now that you understand the genome, now that you know what the genes are, now we're going to talk about the mutations in the UK variant. So here it is. So when you look at all those lines that go from the center all the way to the outside, and you have a dot on the outside, those are mutations. So if you're looking around, starting from the yellow, you'd say, well, there's a couple in the open reading frame. But you know, if you're the virus and you have to grow as the virus, you have to go from cell to cell to cell, what you really want is you want an escape mutation that makes you far more infectious. So that means the mutations in the spike protein are going to be the most relevant. And you notice there is a bunch of them. So let's take a look at it. So when there's an amino acid change, is the new amino acid likely to be the same in size and charge? That is, are we going from a negatively charged amino acid to another negatively charged amino acid? That might mean that they would look about the same, but look what happened. So look at the spike proteins. First, there's two at the top where two amino acids are completely lost. So that's definitely going to result in a change in the winding of this protein. But look at the ones below, the 6. And as you can see, I put polar positive, polar negative. Well, that's a change. What about alanine to aspartate? Non-polar to negatively charged. That's not good either. None of these are the same, actually. Every single one changed the charge or the polarity of the charge of the R group. So, will the change in protein sequence result in enhanced stability of the virus to enter cells? Not for every mutation, obviously, but for some of them, yes. Now let's take a closer look. We're gonna look down. So I'm looking right at this top of the spike protein here. So this is at the receptor binding domain. So if you were going to pick a spot where you didn't want a mutation because it could increase transmissibility, this would be the area. And the touching points are not huge. It's about 25 amino acids in the receptor binding domain that actually touch the host cell. So if you make this spike protein bind better to the host cell, then you're going to get more infection. So that's the big concern. And let me just say that this shows one of the mutations, and this one I call Nancy. It's at 501. And it is in the wrong spot. It is in a dangerous spot. So you can see Nancy highlighted here, and you can see where she is. So remember, it's 3 chains. So if you mutate, you're mutating in all 3. So you're changing the amino acid in each one of the chains. So will a change in the gene sequence result in loss of sensitivity by PCR? Wouldn't this be terrible? That if there was a change in one or more of the nucleotides in the actual gene, that maybe the probe in the PCR assay won't bind anymore. And then every test would be negative. So it turns out for the PCR test that we've been using and for the variants that we have studied, UK variant that's true for South Africa, we're okay. Our PCR assays work. Remember, for a PCR, you see the 3 rectangles in the middle. Those happen to be binding to different genes, and then they're amplified so that there can be detection of that gene. And of course, what we want is to detect SARS-CoV-2, not any other related coronaviruses. And so it'd be very important to know those probes are not hitting at a place where there has just been a genetic change. So we looked at ours, so these happen to be our assays, Hologic Fusion. There's 2 regions of the open reading frame, 1A and 1B. Another one of our assays, the ID Now, Its probe hits at RNA-dependent RNA polymerase. The Cepheid is hitting at nucleocapsid and envelope genes, and the Abbott M2000 in the polymerase and the nucleocapsid. So if you look here at these pictures, there's RNA-dependent RNA polymerase. Notice there's no mutation in the UK variant that's going to cause us a problem. So fortunately, all our PCR assays were fine. I will tell you that 3 or 4 PCR assays were found to be problematic. So you have to make sure, you might even check where you work to make sure that those are not the ones that have become insensitive with any of the variations. Now, remember this, we must differentiate SARS-CoV-2 from all the other coronaviruses. And, you know, if you look at this, you say, what, less than 2% mortality? But you see, if the transmissibility is high, if we get a variant that allows this to go into millions and millions and billions of people, then we're going to get millions of deaths, even though it's less than 2%. Imagine if SARS-CoV-1, which had a 10% mortality, and the one that was in the Middle East in 2012, were pandemics across the world with those mortalities, we would have wiped out a significant population of the earth. And it's still been problematic where we've lost millions. I think it's also worth mentioning here, notice the 4 viruses above where it says severity is mild and mortality is less than 1%. People have gone back to look at a Russian pandemic in the early 1900s that they thought was because of the flu. And as it turns out, that Russian pandemic may have been a result of one of those first 4 coronaviruses. So we're just beginning to learn about this kind of pandemic, but it could be coronaviruses are really susceptible to causing pandemics across the globe. The good part is we have figured out how to not just make the usual viruses where we inactivate the virus or we take the gene from the spike protein, put it inside a virus that causes a cold or very little infection at all, like an adenovirus. And so maybe we can do it that way, but gee, this whole idea of an mRNA vaccine means that we're injecting something, mRNA, that's got a sequence, mRNA, that's going to lead to different amino acids. So when the amino acids change in the world, in the body, because there's been a genetic mutation, we can take the virus, change the nucleotide, so that then it causes an immune response to the new variant. So I think we can stay ahead of this. I'm very excited about the fact that if we understand this at the nucleotide level and at the amino acid level, we can keep up with this. Do I personally think, after reading all this, that we're going to be getting a booster, and the booster is going to have induction of immunity to the variants? Absolutely. And I know that the companies are working on this exact issue right now, facing the changes that you're learning about right now. So it turns out that there are lots of PCR assays. One thing that a lot of people glossed over in the first place is that the PCR assays have different sensitivity. So it depends how much virus is in your body, whether or not the test turns positive. So we're worried about picking it up at all. But remember, we live in a world right now where there's a lot of PCR tests, and I want to show you the variability in this set of slides that's coming. So take a look on the far left column. This is nucleic acid units that are detectable. And you'll see the company and the test. And so let's just take a look. The first one there is 180 units per mil. So if you have just a little bit of virus, that test is positive. What if you have 200? Well, the second test is not going to be positive because it takes 600 units to turn positive. So 180, take a look at the one at the bottom of this slide. That is 10 times, takes 10 times more virus to give you a positive. What about these? Now we're talking about, oh my gosh, you got a 36, that's 20 times. How about 5,400? That's an Abbott molecular assay. So now we're talking 30 times more virus required to turn it positive, and that's still one of the better assays. So as you go up the list here, you can get to ones that are 180,000, which means that you have to have 1,000 times more virus to turn that test positive. So when people say, oh, we got issues related to sensitivity, false positive, false negative, you bet you do. You bet you do, and most doctors don't really know when they see positive or negative, if they're really talking about positive or negative. So, here are a few more at 180,000. Takes a lot of virus to get these positive. So I drew this in a picture. If you're the green dot, meaning that's how much positivity you have, that's how much virus you have. If you're above the line for a test, you're positive. So it's above the line for test A, the green. So you're positive for test A. But you're below the line for test B, C, and D. So you get a positive, and if we did that on 3 different assays that required more virus, you'd be negative, negative, and negative. What would we probably tell you? You're negative. Go home, join your family, go out and work on the platform in the Gulf, right? So I think it's important to understand that there's tremendous variability in the sensitivity of these assays. So we have to have the assay. Just to say this, the assay must work. Wherever we did well in the world with a near elimination, it was all because there was so much testing. And the idea that, oh, we shouldn't test because we're going to find positives is absolute lunacy. That is the whole goal of shutting this down. So, will a change in the protein sequence in the spike protein result in a failure of the vaccine? So, let's get into this really important question. And there are not a lot of vaccines. Notice there are 3 in the U.S. We have the Pfizer, the Moderna, and the Johnson & Johnson. And the Johnson & Johnson is a one-time shot. It's not an mRNA vaccine. There are 3 other vaccines in the world that are listed on this slide. So they're prepared in different ways, a lot of them, by putting the spike protein gene inside an adenovirus gene sequence so that you can get it inside cells. But the mRNA viruses are Moderna and Pfizer. And that's brought a lot of excitement to the whole idea of vaccinology. So let's take a look at some of these changes in the protein as a result of the mutations in the UK variant. So I've already told you that if you change the sides of the spike protein, even though this isn't in the receptor binding domain, if you're in the sides of the spike protein, those antibodies were helping you stop being infected. So the mutations for the 2 amino acids that get deleted, that had a bad effect. And here's the other deletion, 144, 145. They were hitting at the wings of the spike protein, where you'd get an antibody that would stick on here. So if I could stick this on right here, then you'd see there's an antibody in the way, and it can't roll over and get into the cells. So what about this one? This one is way further down. It's right at the area where S1 transitions into S2, and it is still relevant. So let's go to the South African variant, which really taught us a lot, because now it's become different enough that there are concerns about the vaccine. So, is the variant the South African vaccine from the one from Wuhan? Is it from Doug? Is it from a UK variant? So we're going to look at that too. Now, here is a picture of the spike protein gene and the mutations that result in amino acid changes in the spike protein gene from the South African variant. And notice that there's another really important one right here. And this particular one is Eric with a K. So Eric has connected with Nancy, as you can see. And now we have with Eric the mutation that results in a glutamic acid, negatively charged, going to a lysine. I mean, that totally changes the rearrangement. When I stick out my hand and I'm supposed to grab another R group from some part of the chain, and I'm switching from negative to positive, that linkage is not going to occur. So the Nancy mutation, the one that starts with N501Y, helps the spike protein enter the cell. So you can see among the list of amino acids that we're really changing things when we have something like Eric. And so Eric, in this case, is taking us from glutamic acid to lysine. So take a look now at these pictures. And on the top, you'll notice the host cell. So now the version of this is that the host cell is on top, like so, and the spike protein that we're looking at is coming in from the bottom. So, so when you look at the receptor binding domains and you say, what is in the way? Then what you can see here is you can see that Nancy is definitely right there in the receptor binding domain, as is Eric. So if you change the amino acids at those points, it's either going to make it easier to get inside the cell or harder. Now, you've seen this picture before about rising. It was different mutations, but goodness gracious, the change happens very quickly. And when we got the South Africa variant, really what concerned us a lot was that the AstraZeneca vaccine, not that we were using it, but it looked like it was providing minimal protection. Maybe it would keep you from death, put you in an ICU. Maybe it would take you from an ICU to a regular hospital bed. But it wasn't the efficacy we were enjoying with Moderna and Pfizer and Johnson & Johnson. So, so now what's emerged after UK and South Africa? A whole bunch of other variants. So I want to take you through a few of them. Here's a California variant. And you'll notice there's a couple of mutations in the open reading frame, 3 in the spike protein that are listed here, defined by these 5. There are more. But the one that is the biggest concern is Lamar. Lamar 452 spike protein. And if you just look at this, you understand why Lamar is so important. Doggone it, he's right here in the receptor binding domain. So if you take a look at this picture, who are the bad actors? Eric, Nancy, and another one called Karen. So this is a Brazilian version. Karen showed up in the Brazilian version. And when you put those 3 people together, bad things happen, right? Now let's take a look at who's becoming what. So when you get down to B1, it looks like there were precursors, right? I mean, there was some ultimate genome, and then it broke into a few. And so which ones grew? Which ones developed? So when you got down to B.1, that was Doug. And what happened is B.1, Doug, pretty much populated the United States and took over. The South Africa variant comes from Doug. And you'll notice that some of these others, California and New York variant, also come from Doug. Now, Doug led to another variant, B.1.1, and now you can see that's Kent, that's the UK variant. And then if you go over to the right side, there's the Brazil variant. So variants are emerging from variants, right? So that's why I said it's really getting complicated now. So when you have 41,000 mutations that have been documented, 880 lineages, now you're saying, how do you make sense of it? Well, you have to find out what's dangerous. So less than 10 of the mutations make the virus more dangerous. So yeah, there are a lot, but what do? We'll classify them, and we'll make it more severe. So you could have a variant of interest, meaning we're paying attention to you, a variant of concern, we'd like to do something about you, and a variant of high consequence is, are we going to make this pandemic start all over again? So the interest ones, specific genetic markers have been associated with changes to receptor binding. That's important. Reduced neutralization by antibodies, okay, which are generated by a previous infection or vaccination. Reduced efficacy of treatments like antibody, potential diagnostic impact that screws up the PCR, or predicted increase in transmissibility or severity. Those are really important, right? And so I highlighted in yellow, this is a variant that appeared in New York. And I'm just looking at spike protein variants, omitting the others for a minute. And I highlighted in yellow the ones that are gaining increasing attention. And you'll see that there are certain bad actors showing up over and over again. So Tammy with an I is a problem in this New York variant, but doggone it, there's Eric and there's Doug. Now, these are variants of interest, not yet variants of concern. Here's another variant of interest, also in New York. And what does that have? Now we have this mutation that leads to the loss of 2 amino acids. That's the delta 144Y. But there's Doug again in the New York mutation. Here now is the Brazilian variant. So the Brazilian variant is still just a variant of interest. But there's Eric and Doug. There they are again. Now, variants of concern, there's one more piece here, and it's the second point. You get more severe disease, so increased hospitalization or deaths. So this is really the important part. And this slide shows a list of 5 different variants. And you'll notice on the far right, the first one is the UK variant, then the Brazil, South Africa, 2 in California. And if you look at the names, right, so it's the deletion all right, but there's Eric, Nancy, and Doug in the UK variant. In Brazil, Karen, Eric, Nancy, and Doug. South Africa, Eric, Nancy, Doug. And then in California, we have Lamar and Doug. And then Lamar and Doug in the other California variant. Fortunately, we don't have any variants of high consequences yet. So we may get to this, but if we do, we're starting all over again. And the trick is, please get vaccinated so that we don't have anybody sitting around being an incubator for the next variant. So look what happened in the U.S. How do we get taken over? We're now full of the UK variant, and it just happened really, really fast. So now it's the dominant variant. This picture, as it goes left to right, shows sequence of time, and the UK variant is in the tan color. And if you just look, those are 2-week intervals between the bars. The UK variant back in January was tiny, and now it's the dominant one, more than 50%. So when the variant occurs, if there's increased transmissibility, that's the one to worry about. This is just a table where I put the 5 arrows pointed to the variants of concern. So we have 5 here, and the goal, of course, is to figure out how to immunize ourselves to these and collect enough people who are not going to spread the infections. Now, the ones that really have been important at the receptor binding domain are Nancy, Eric, and Karen. And this picture, I just wanted to show it to you because it was so good. This is looking down at the receptor binding domain. I'm looking down at it. There it is. And what they did was they drew this picture where they have white balls. And if the white ball changed to a red ball, then what that meant is that you no longer could immunize and get an antibody to that site. So you want as many of these sites occupied by the clips that would prevent the infection. And so what if, there it is, I can bind an antibody to that receptor binding domain, but then when I get the mutation that changes the amino acid, the antibody can't bind. So as you can see, a bunch of those, 1, 2, 3, 4, some in there, that went from white to red, can't bind the antibody there anymore. And this is where we really want to cluster up those antibodies. So if you look at this and see the variety of mutations here, I've highlighted Eric, Karen, and Nancy. And the ACE2 is the receptor for the host cell, and the bottom part there is the spike protein. So there have been many now spike protein gene mutations. Look at this. Remember we talked about all the mutations, the thousands of mutations, and this just shows you many of them, most of them, are going to be in the receptor binding domain, because if the virus is going to escape, that's what it wants to change so that it can bind better. Now, I did tell you that the nucleocapsid protein and gene are studied as well, and you would say, well, is there pressure to change the nucleocapsid protein so that the antibodies don't wipe it out? Well, it turns out it's done a lot of mutating. So these are the different segments all in the nucleocapsid gene that have changed, and all the red dots are places where there have been mutations. So it's not just the spike protein, also nucleocapsid, but really all the vaccine attention has been to the spike protein. So what have we learned in the detection of clinical importance for SARS-CoV-2? A molecular test is better than an antigenic test. Antibodies to the spike protein occurred, also to the nucleocapsid protein, or both. The neutralizing antibody, the one that hits in the spot that stops infection, which is not just any old antibody, but certain ones have the ability to stop the infection. Those are really the important things. We don't measure that. We're just measuring antibody that's been generated, although there may be neutralizing antibody tests for the general population emerging. And sequence variation of viral RNA we have to stay on top of. So whenever somebody gets infected, we have to keep sequencing to see if it's a variant. So The vaccines are different. SARS-CoV-2 genome has multiple known variants, and so is there a consensus on which vaccine works for which variant? I just want to show you a little data. We have a little bit of information, and of course we have real-world information, meaning that if you go to a country and say, the dominant variant is this, and the vaccine's not working, that's real world. But we can do things in a test tube where we can actually look at it and say, hey, would this antibody knock out this variation? So we can make a new vaccine in about 6 weeks. Surely we'd get rapid approval, but let's see where we are. And South Africa, that variant woke everybody up. If the line goes higher to lower, it means that there's less efficacy. So if you were infected originally, this is the one on the far left, originally infected by Doug, and you got better, and we got your plasma, and you had antibodies to the Doug version, how well would those antibodies knock out the South African version, which is the one on the right? Well, less so. Did it work? Yes, but less so. What if you got infected by the UK variant, and then the South Africa variant came along, and you went to a party, and somebody had the South Africa variant? Well, you got some antibodies because you were infected by the UK variant, but it doesn't work quite as well. What if you got the Pfizer vaccine? Well, again, if you had the early Wuhan isolate, meaning not even Doug, before Doug, and you look at the ability of Pfizer to knock it out, it is much better at knocking out the Wuhan variation, the first thing we had back in February, and less so for the South African variant. And what happens if you have AstraZeneca, which is the one that came to everybody's attention? And you can see the lines also go down. Now, people had this other great idea, and that is maybe we could make a protein with the mutations in it and see which mutations are going to really affect antibody binding. So what if you took a UK version and put just Nancy in it, and it turns out the antibody from the vaccine works fine, maybe even a little better. What if you put Nancy and Doug and the deletion at 69 and 70 where you lost 2 amino acids, and you lost those, the antibody's doing fine too. But in that South African variant where you combine Nancy, Eric, and Doug, now we got a problem. Now we're not binding the antibody as well. See how we're dissecting it piece by piece, amino acid by amino acid. So we're figuring it all out. Let me just say, there's also a concern about why did 15 people went to this party and none of them were infected, and an infected person came and 10 got sick, but 5 didn't, and the 5 were talking to the infected person the whole time. And we're beginning to realize that there's something in us as hosts, and the host has certain mutations potentially that make them more likely to get sick. And you can see 5 of them here. So if you have a mutation in, I'll pick the last one, the interferon receptor gene, and you went from a thymine to a cytosine for your base, that change in that gene in your body as the host can make you more susceptible. So it's not just the virus changes, it's also us, again, adding to the complexity. So I hope now you have a good understanding of the virus and how it's constructed. You understand the specifics of this spike protein, S1, S2, receptor binding domain. You understand how the infection occurs. You got a good idea, especially good idea of the UK and South African variant, and then all these other variants and how they're being classified. So thank you very much for listening, and next year we're going to do it for real.